Okay. Okay, so chapter 10. Okay, what's going on here? I thought. Okay, so chapter 10 is published, so let me bring it up on the screen. Oh. Okay. So I could have shown you this. Okay. All right, so basically chapter 10 deals with energy changes and other related topics. And I would say that the main equation, so that I can get my pen here, the main equation that you need to be concerned with in this chapter will be what I'm about to write on here, which is okay, which is Q is equal to M times C times delta T, right? That's the equation that you'll be concerned with for pretty much this chapter, right? So if you watch the videos, they talk about the definitions of heat and energy and all that. I won't go into all that right now, because basically what I'm concerned with is solving the problems that are provided in this assignment. And the main equation you're going to use for solving this, all the problems here will be this right here. So let me remind you of what these different terms represent. This here, Q, represents the amount of heat that is added or lost by a substance. M is the mass. Delta T is the change in temperature. And C here is called the specific heat. All right. Now the specific heat, the definition is given in the video. It is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. That's the definition of specific heat. And different substances will have their own unique values of specific heat. So specific heat is basically a physical constant. Just like density, melting point, boiling point, refractive indices, and so on, which different substances will have different values for. The same is true for specific heat, right? Now, in terms of units, using the SI system or the metric system, the unit of heat is joules, the unit of mass will be in grams, and the change in temperature in terms of the unit can be either degrees Celsius or Kelvin. It doesn't really matter, numerically speaking, what the values are in degrees Celsius or Kelvin. The point here is that the change in temperature will be the same numerically, right? And therefore, based on these units, if you were to arrange this into this arrangement here, where we express C in terms of the other terms, C would be equal to Q over M times delta T, right? So as I said before, Q is in joules, delta T would be in degrees Celsius or Kelvin, and M would be in grams, which means that the unit of specific heat would be joules over grams degrees Celsius or joules over grams Kelvin. It doesn't matter which one we use, numerically, the result would still be the same. And since water is the most common substance when it comes to these problems, at least at this level, the specific heat of water is equal to 4.18 joules per gram degrees Celsius. And water, by the way, I don't remember if I mentioned this in the videos, but water, of all the substances that are commonly encountered, water has the highest specific heat, all right? And there's a phenomenon behind that known as hydrogen bonding, which is responsible for that. Metals, they tend to have low specific heat, right? So it's not uncommon to encounter a metal that would have a specific heat around, I would say, 1 point something or even less, all right? Okay, so with that said, so as I said before, this is the equation that you'll be working with for the most part when it comes to solving these problems. All right, so let me clear this. And let's start with question number 1. And it says a 15.75 gram piece of iron absorbs this amount of heat. And it says the temperature changes from 25 degrees to 175 degrees. Calculate the specific heat of iron. So basically, as I said before, we're using Q is equal to M times C times delta T. But what the question is asking for is C. So C would be equal to Q divided by M times delta T. And then we plug in the numbers. Now Q is this right here, 1086.75 joules, divided by M, which is 15.75 grams, times the change in temperature. So the initial temperature is 25, the final temperature is 175. So the change in temperature will be the difference between those two. And that's it, that's the setup. Of course, I'll work on what's within the parentheses first, which will be 150 degrees Celsius, and then we do the rest. So that would be 1086.75. Oops. 1086.75 divided by 15.75 times 150. And according to my calculation, this works out to be equal to 0.460. And the units here would be joules over grams degrees Celsius. And that's basically it. Right? Any questions about this? Any questions? Okay, so that's number 1. Number 2 is asking for the amount of, oh, by the way, before I move on to number 2, let me just say that one common error that students tend to make when they're learning this for the first time is that they confuse this specific heat with the heat. All right, they put the numbers in the wrong places, in other words, right? So please remember that Q represents the heat and C is the specific heat, right? Don't confuse the two, all right? Okay, so let me clear this here and scroll down to number 2, which says, how many joules of heat are needed to raise the temperature of 10 grams of aluminum from 22 degrees Celsius to 55 degrees Celsius if the specific heat of aluminum is 0.90 joules per gram degree Celsius? So again, you'll be using the same equation. In fact, you'll be using this form of the equation here because the question is asking for Q, all right? They gave you the mass. This gives you the change in temperature. And this here is the specific heat, right? So it's all a matter of plugging the numbers in. So the mass is 10.0 grams times the specific heat, which is 0.90 joules over gram degrees Celsius, times the difference in temperature, which is 55 degrees Celsius minus 22 degrees Celsius. And that's it. Again, I will work out what's within the parentheses, which would be 33 degrees Celsius, and then do the rest. So that's 33 times 0.9 times 10. And according to my calculation, now this I would have to round off to 2 sig figs. So the answer would be 3.0 times 10 to the 2, and the units will be joules. And by the way, another thing I should highlight here is that when you're doing these calculations, make sure that you include the units as a part of the whole process so that you can see what units will cancel out. For example, here, the grams will cancel out here and here, degrees Celsius will cancel out there and there. So the only unit remaining would be the joule unit, and that's it. All right? Okay, any questions about this one? Any question? All right. Any questions out there in Zoom?
Why are we dividing 0.9 joules by 9 degrees Celsius?
No, that's not 9. I'm sorry. That's my poor handwriting. That should be grams.
Oh,
I apologize for that. I'm not known for my artful handiwork when it comes to handwriting. Okay, any other questions? Any other questions? All right, so let me clear this here and scroll down to number 3. And number 3 says, to what temperature will a 50.0 gram piece of glass raise if it absorbs 5,275 joules of heat, and the specific heat is 0.50 joules per gram degree Celsius. And it says also that the initial temperature of the glass is 20.0 degrees Celsius. All right, so this is a bit different from the others that we have just looked at. Again, we're going to use the same equation, right? So the equation we're going to use here is Q is equal to M times C times delta T, right? Now, because the question is asking to what temperature, and they gave us the initial temperature, what I would do is try to solve for delta T, because delta T would give us a change in temperature, right? So basically, once we find a change in temperature, we just add it to the initial temperature, and that would give us what the question is asking for. So delta T, based on this equation, would be equal to Q over M times C, all right? So we plug the numbers in. Q is 5,275 joules divided by M, which is 50.0 grams, times C, which is 0.50 joules per gram degree Celsius, all right? So let's do that calculation. So that's 5,275 divided by 50 times 0.5. And according to my calculation, this works or no? This I have to round off to 2 sig figs. So that would be 2 sig figs, that would be 210 degrees. No, wait a minute. I did. Oh yeah, 210 degrees Celsius. All right. So that would be the change in temperature, right? Now the question says that the initial temperature of the glass is 20 degrees. So the final temperature would be equal to the initial temperature plus the change in temperature, right? So the initial temperature is 20 degrees Celsius. And I'm going to add to that 210 degrees Celsius. And this works out to be equal to 230 degrees Celsius. And that would be the final answer, all right? Okay, any question about this? Any questions?
I did the evaluation on the
Okay, which part? You're talking about this part right here?
Yeah.
Okay, let me do it again. What answer did you get?
I got 52.30.
Okay, let me do this again. 5,275 divided by 50 times 0.5. I got 211, which I rounded off to 2 sig figs to get 210. So I don't know. I don't know what error you made. I don't think this time I've made an error. Anybody else get something different? Or got the same as what I did, what I got? When I did this part here, when I did this here, the answer I got on my calculator display was 211. And then I wrote it off to 2 sig figs. Okay, any other question about it? Any other question? All right, now, number 4, let's see what, based on what we have done so far, here, you guys should be able to do number 4. Sure?
Oh, I think
Oh, okay. What did you do wrong?
okay, well, first I, for the divide part, I actually pressed the divide button. What you did was this behavior fraction.
Oh, okay. All right, so let's hear what you guys have to say about number 4. Again, you're using the same equation. Q is equal to M times C times delta T. All right, so let's hear what you guys have to say about this one. What's the question asking for? And you guys out there in Zoom, please feel free to contribute to the discussion. What's the question asking for?
It's asking for the heat capacity of a piece of wood.
Right, so that would be one of these terms in this equation? C, exactly. So I would say C is equal to Q over M times delta T, right? Okay, so what is heat? Based on the information provided in the question. Q.
Q is 6.75 times 10 to the 4th.
Okay, very good. And then what is M? $1,500.0 grams times, now we get to the delta T, which is a change in temperature. So what's the change in temperature? 57 degrees Celsius minus 32 degrees Celsius. And that's it. So let's work out what's here first. So 57 minus 32 gives 25 degrees Celsius down here. And then let's do the rest, which would be 6.75 times 10 to the 4 divided by 1,500 times 25. And according to my calculation, so how many sig figs? 2 sig figs. So according to my calculation, the answer is 1.8, and the units would be joules over gram degrees Celsius. And that's how that is done. All
Why
right?
do we mark it as grams over, well, why do we mark it as joules over grams degrees Celsius?
Because you have the joules here in the numerator, in the setup. You have the grams down here and degrees Celsius down here in the denominator. So you put them together like this.
Oh.
Mhm. All right.
Thank you.
Okay, any other questions? Any other questions? Okay, let's clear this. And let's scroll down. Now, this question, it says 100.0 mils of 4 degrees Celsius water is heated until its temperature is 37 degrees Celsius. It says that the specific heat of water is 4.18 joules per gram degree Celsius. Calculate the amount of heat needed to cause this rise in temperature, and it gives you an additional piece of information that the density of water is 100 1.00 grams per mil. All right. So again, same equation. Q is equal to M times C times delta T, right? So they gave you C. So this is C here, right? And they gave you the initial and final temperature, right? So you can get delta T from that. The only thing that is not given directly is the mass, right? However, you can calculate the mass. Why? Because they gave you the density of water and they also gave you the volume of water, right? And we know the relationship between density and volume, right? Density is equal to mass over volume. So if you want to get the mass, you're going to multiply the density by the volume, right? So once you multiply the density by the volume, that gives you the mass, which goes here, and then you can do the rest of the calculation, and that would give you the answer, which is the amount of heat energy needed to raise the temperature to 37 degrees. So basically, we're going to start off with Q is equal to, as I said before, the mass is the same thing as density times volume. So the density is 1.00 grams per mil, multiplied by the volume, which is 100.0 milliliters. And then so that part here will give you the mass. And then I'll multiply by C, which is 4.18 joules per gram degrees Celsius, multiplied by the change in temperature, which is 37 degrees Celsius minus 4.0 degrees Celsius. And that's basically the setup. So 37 minus 4, that part will give you 31 degrees Celsius. And then we need to do the rest. So 1 times 100 times 4.18 times 31. And I need to round this answer off to 3 sig figs. So according to my calculation, Q works out to be equal to 1.30 times 10 to the 4 joules. Let me do this again, just making sure that I did everything correct. 100 times 4.18 times 31. Okay, so that's what I got. 1.30 times 10 to the 4 joules. Right? Okay, any questions about this one? Any questions? Any questions? All right, so let me hear what you guys have to say about number 6, I'm sorry. Let me clear this.
Did you subtract 4 from 37?
I'm
Just a
sorry?
moment ago. Did you subtract 4 from 37 just a moment ago?
Oh, okay, I think I just realized that already. Let me, yeah, yeah,
Sorry.
I think I may have made a mistake. Now that you mention it. I'm trying to bring this back. How do I bring this back over there? Okay. That should be 33, not 31. Thank you. Who was that? I'd like to give credit to whoever.
Audrey.
Audrey, thank you, Audrey. Okay, sorry. Um, so that should be 33. So that means that the answer I got is incorrect. So let me redo this calculation here. So that's 100 times 4.18 times 33. Okay. Oh, 100 times 4.8 times. Okay, so this time I got 1.38 times 10 to the 4. All right. Actually, it should be 1.4 because this should be 2 sig figs. So again, let me correct myself. So this should be 1.4 because I have to round up to 2 sig figs because of the 33. All right. Okay. All right. So let me clear this and scroll down to number 6. All right. So let's hear what you guys have to say about number 6. They gave you the mass of mercury. They gave you the initial and final temperature, and they gave you the amount of heat. And the question is asking for the specific heat of mercury. So how would you approach this problem? Start. Okay, so C is equal to Q over M times delta T, all right? Okay, so what's Q? 455 joules divided by the mass, which is 25.0 grams, times the change in temperature, which would be 155 degrees Celsius minus 25 degrees Celsius. 6.25. I'm sorry? Oh, no, this is, I'm sorry, yeah, this is just the number of the question. It's 25 grams. Okay, so this part here works out to be 130 degrees Celsius. So 455 divided by 25 times 130 and round it off to 3 sig figs. So I got 0.140 joules over gram degrees Celsius. And that's how that is done. All right, any questions about that one? Any questions? Okay, number 7 is saying, Oh, basically it's the same thing. Oh, okay. I did not mention this. There is the non-metric unit of heat, which is known as calories, right? And the relationship between the calorie unit and the joule unit is 1 calorie is equal to 4.18 joules, right? So that is provided in the handout that you have when you're doing your test, all right? So you don't need to memorize this. But that's the relationship between the calorie unit and the joule unit, right? So this question is asking for the specific heat capacity of a silver metal. It gives a mass, it gives the amount of calories of heat, and it says the temperature rises 15 degrees Celsius, right? So again, we're using this equation. C is equal to Q over M times delta T. So Q is equal to 47.3 calories, right? Divided by M, which is 55.00 grams, times the change in temperature. And the question says that the temperature rises by 15 degrees Celsius. So 15.0 degrees Celsius. So that's a setup. So 47.3 divided by 55 times 15. And according to my calculation, this works out to be 0.0573, I'm going to say, 363. So 0.0573 calories per gram degree Celsius, right? So you can leave the answer like this because the question did not specify the units, right? If the question asks you to do the calculation so that the final answer is expressed in joules per gram degree Celsius, then you'd have to add this conversion factor where we have 1 calorie down here, 4.18 joules up here, and that will give you the answer in joules per gram degree Celsius. So that means I have to multiply the 0.0573 by 4.18. And according to my calculation, I got rounded up to 3 sig figs again. I got 0.240. So both of them are correct. If the question specified a particular unit, then you have to make sure that you express your answer in that unit. All right. Okay, any question about this one? Any questions? Questions?
How many joules in a calorie again?
Right here, 1 calorie is equal to 4.18 joules. And as I said before, that is provided in the handout, with the tables and other information. So you don't have to memorize it, but that's the relationship. Okay, any other questions? Any other questions? Okay, let me clear this. Let's go down. Okay, now this one says if a sample of chloroform is initially at 25 degrees, what is its final temperature if 150.0 grams of chloroform absorbs 1.0 kilojoules of heat and the specific heat of chloroform is 0.96 joules per gram degree Celsius? Okay, so let me hear what you guys have to say about this one. What's the question asking for? What's the question asking for?
The change in temperature plus 0.1.
Okay, all right, that's okay, good, right. You're absolutely right. Basically, the question is asking for the final temperature, which would be the initial temperature plus the 25 degrees Celsius. You're absolutely right. Okay. So, what next? What would you do next?
Q equals M times C.
Q is equal to M times C times delta T, right? But I would arrange this into something else.
T is equal to Q.
Delta T. Oh, I made a mistake here, by the way. This should be delta T, not Ti. Ti is the initial temperature, which is the 25 degrees, which is the 25 degrees Celsius. So let me correct that. So this should be delta T right here. Okay. So delta T will be equal to what? Q over N times C. Very good. So let's calculate delta T. Q is what? 1.0 kilojoules, right? What I would do is convert that to joules. So 1 kilojoule is equal to 1,000 joules, right? And then divide that by M. What is M? M is 150.0 grams times C, which is right here, 0.96 joules per gram degrees Celsius, right? So let's do this calculation. So basically that's 1,000 divided by 150 times 0.96. And according to my calculation, this works out, I'm gonna say fix, 2 sig fix, so 6.9 degrees Celsius, right? So that's delta T. So therefore, to get the final temperature, that would be equal to delta T, which is 6.9 degrees Celsius, plus the initial temperature, which is 25 degrees Celsius. So that would be equal to, round off to 0 decimal places, so that's 32 degrees Celsius. And that's how that is done. Right? Okay, any questions about this one? Any questions? Any questions? Okay, now for the next question, it says, how much energy must be absorbed by 20 grams of water to increase its temperature from 283.0 degrees Celsius to 303 degrees Celsius. Okay, so basically it's a direct application of this equation right here. So Q in this case will be equal to M, which is 20.0 grams, times C, which is 4.184 joules per gram degree Celsius, times the temperature change, which is 303.0 degrees Celsius, minus 283.0 degrees Celsius. So let's see what that gives. So when I work out what's going to do the parentheses first, I got 20.0 degrees Celsius, and then I'm going to multiply that by 4.184 times 20.0, and this needs to be rounded off to 3 sig figs, so that would be 1,670 joules. And that's how that is done. Right? Any question about this one? Questions? All right, let me clear this. Scroll down. Okay. All right, I'm going to skip number 10. You guys should be able to do number 10. So I'm going to leave that for you to do on your own. If you have any problems, let me know. But let's look at number 11. Number 11 says object A has a specific heat of 2.45 joules per gram degree Celsius, and object B, its value is 0.82 joules per gram degree Celsius. Which object will heat up faster if they have the same mass and equal amount of heat is applied at the same rate? And explain why. All right, so this is a kind of conceptual type of question, right? They gave you the specific heat values, right? And assuming that they have the same mass and you apply the same amount of heat to both of these substances, which would you expect to heat up faster? I think that's what the question is. Which would you expect to heat up faster? So let me hear your response and let me hear your explanation. Which one would you expect to heat up faster? Is it object A or object B?
B.
B, okay, let's hear your reasoning.
Because it requires less energy to get hot than object A.
Okay, so let's start off with the values. So you're saying that given a mass is the same. Because B has a lower specific heat value, that means that less heat is required to heat B compared to A to the same extent, right? So therefore, you'd expect that over the same period of time, the B would heat up at a faster rate. And that's pretty much it as far as the answer for that question is concerned. So let me just write this down here. B will heat up faster because based on delta T is equal to Q over M times C, right? The one with the lower specific heat would have a greater increase in temperature at a faster rate. So you heat up faster because based on this, the having the lower C value, that implies that it will experience greater temperature change over the same time frame, for lack of a better expression. Okay, so that's basically how I would word it. All right, so that's it for question number 11. All right, scrolling down. Okay, now this one is interesting here, number 12. All right. Number 12 says, if a piece of aluminum with a mass of 3.99 grams and a temperature of 100.0 degrees Celsius is dropped in 10.0 centimeters cube of water at 21.0 degrees, what will be the final temperature of the system? And the hint, well, one hint is given, and that is that the density of water is 1.00 grams per mil, right? And this is kind of, we met this earlier when it comes to getting the mass using the density and the volume. Okay, let me clear this here. Now let me explain what's happening in this case so that you can understand how to approach this problem. So we have a situation here where we have aluminum, which is at a high temperature, 100 degrees Celsius, right? And we have water here, which is at a significantly lower temperature, okay? So you're adding the hotter metal to the cooler water, right? What's going to happen is, and this was discussed in the videos, you're going to have a heat transfer, right? Where the metal will be giving up its heat to the cooler water, right? And that's basically what happens in each case where you have a hot object in contact with a cooler object, right? So basically, the first thing we can write down mathematically is that the heat that is lost by the metal will be equal to the heat that is gained by the water, right? So what's going to happen is that the temperature of the metal is going to fall because it's losing heat, and the temperature of the water will rise until you get to a state of what we call thermal equilibrium, where the temperature of both the metal and the water are the same. So when you get to that point, there is no more heat transfer, right? So what the question is asking for is that final temperature, right? So what I'm going to do is write down, now remember, we said that Q is equal to M times C times delta T, right? So what I'm going to do is write down this expression for each of these terms, right? So for the metal, that would be the mass of the metal times the specific heat of the metal times the change in temperature of the metal, right? And that would be equal to the mass of the water times the specific heat of the water times the change in temperature of the water, all right? Now, what am I going to do? Okay, so let's put in the numbers. The mass of the metal is 3.99 grams times the specific heat of the metal. Now, that should be given in this question, which is not given. And I think that actually is given in an earlier question, if I'm not mistaken. Let me do a quick check here. There was one question we did earlier with aluminum. Where is it? Okay, aluminum is 0.90 joules per gram degree Celsius. So 0.90 joules per gram degree Celsius. So that information, you cannot solve that problem without that information. So let me scroll back down to the question that we were working on. Okay, so then we get to the temperature change. Now, we don't know what the final temperature is, right? But we know that the initial temperature is for the metal 100 degrees, right? 100.00 degrees. So here I'm going to put 100.0 degrees Celsius minus the final temperature. This is what we're trying to find, right? Okay, on the left side of the equation now, I'm going to put, for the mass of the water, I'm going to put, now to get the mass of the water, we multiply the density by the volume. So that's 10.0 centimeters cubed multiplied by 1.00 grams centimeters cubed. So that combination will give you the mass times the specific heat of water, which is 4.18 joules per gram degrees Celsius. And then we're going to multiply by the change in temperature of the water, right? Again, we don't know what the final temperature of the water is. So that would be TF, the same as the final temperature of the metal. But the initial temperature of the water is 21.0 degrees. So therefore, it's going to be TF minus 21.0 degrees Celsius, all right? So what I'm going to do now is work out what this gives. In fact, you know what? Let me do this. I'm going to divide both sides by 3.99 grams times 0.90 joules per gram degree Celsius. So 3.99 grams multiplied by 0.90 joules per gram degree Celsius. Okay, and then let's see, some units will cancel out here and here, grams will cancel out here and here. All of this will cancel out all of that. All right, so let's see what this gives. 10 times 1 times 4.18, and then divided by 3.99. Okay, so based on my calculation, this works out to be equal to, when rounded off to 2 sig figs, we'll do this again. 10 times 4.18 divided by 3.99. Okay, so what I got here is 12. When I round off, when I work out all of this here, that's 12 rounded off to 2 sig figs times TF minus 21.0 degrees Celsius. And over here, because all of that cancels all of that, I'm going to end up with 100.0 degrees Celsius minus TF is equal to this right here. And basically from here is just a matter of doing some algebraic steps. This is here because I'm going to need space. Okay, so what I'm going to do now, I'm going to, what's the term they use in math? Is it distribute, where you multiply this? Okay, so by everything within the parentheses, you're going to end up with 100.0 degrees Celsius minus TF on the left side, and then on the right side, you're going to have 12 TF minus 12 times 21.0. So 12 times 21.0 gives 250, rounded off to 2 sig figs. So that would be 250 degrees Celsius. And then we're going to get like terms on the same side, which means that, okay, I'm going to add 250 degrees Celsius on both sides, so that this goes in that. And then I'm going to add TF to both sides. So that this goes in that. So here I'm going to end up with 350 degrees Celsius is equal to 12 plus 1, 13 TF, which means that TF will be equal to 350 degrees Celsius divided by 13. And let's see what that gives. 350 divided by 13. And according to my calculation, rounded off to 2 sig figs, that's going to be equal to 27 degrees Celsius. All right? And I'm fairly confident that this answer is correct because 27 degrees lie between the 100 degrees, which was the initial temperature of the metal, and the 21 degrees, which was the initial temperature of the water. So 27 lies within that range. So I'm fairly confident that that answer is right. And I mentioned that to say that when you're doing these calculations, look at the final answer, see if it makes sense, right? Because let's say, for example, I did this, and I got an answer that is lower than 21, and you added something wrong, because the temperature cannot be lower than 21. It has to be between 100 degrees and 21 degrees, all right? Okay, any questions about this one? Any questions? Any questions? No questions? Now, if you can do number 12, then you should be able to do, or if you understand what we did in number 12, then you should be able to do number 13, because number 13, I think, is very similar, right? Same idea. So I'm going to leave that for you to do as well, all right? Again, if you have any issues, please feel free to let me know. You can call me, or we can have a Zoom talk. So that's pretty much it for today. Let me clear this here. And what I'm going to do is, well, I have an announcement to make, but before I do that, let me open up a Dropbox for this. So this is assignment number 10. And let me okay, so I'm going to let it be due on the 21st. All right, so let me do this as well. Okay, so that's the first thing. The second thing I want to mention is that for the next class, we'll be doing chapter 30. So we're going out of order in terms of the numerical order of the chapters, but in my opinion, it's best that we do chapter 13 after doing chapter 10, because chapter 10 we're dealing with heat and energy, and then you're going to see how that applies to chapter 13, which deals with gas laws. So I've published the videos for chapter 13. So between now and Tuesday of next week, make sure you watch these videos so that we can discuss the problems as far as chapter 13 is concerned. In fact, I've made some copies of the assignment for chapter 13. So if you want to pick up one on your way out, no problem. I have no problem with that. You can use that to help you. If you want, you can try to attempt doing those problems, but we will be discussing this next class. The third and final thing I want to make mention of by way of announcement is that your next test will be on, let me just check the academic calendar so that I don't get the wrong thing. I'm going to post an announcement about that, but I want to make sure I tell you guys in person. So let me see here. According to the academic calendar, okay, so the Thanksgiving break is the 26th. And then we get back on the Monday following. So I'm going to make it the week of December 1st. So from December 1st to December 5th, The test will be available at the testing center, and you can go there, make sure you make your appointment and so on, and do that test. And that test will be based on chapter 7, 8, and 9. All right, so what we cover today will not be on that test. All right, so chapter 7, 8, and 9 will be what test number 3. Let me make a look of that. All right, so test number 3 will be based on chapter 7, 8, and 9. All right. So the date for that will be December 1st to December 5th. All right, so I think that's it by way of announcement. All right, so unless there are any other questions, that's it for today, folks. Oh, first one.
Right, I know you literally just said this, but it's a test on December 1st.
December 1st and 5th. Yes, sir. Yeah, you too. Take care. Oh, someone had a question online. Okay, so, Ms. DeGraw, you're asking if we have a meeting. Yes, we do meet on Tuesday of next week. I just saw your question, so I apologize for that. Is there any other questions here? Okay, all right, so you guys out there in Zoom, I will be signing off right now.